Audio Jungle.
Dear viewers, today we'll be going to discuss about the Kirchhoff's laws. So, these laws are more comprehensive than Ohm's law and are used for solving electrical networks which may not be readily solved by the latter. Kirchhoff's laws, which include the Kirchhoff's current law and Kirchhoff's voltage law, is a useful way for determining the equivalent resistance of a complicated network of conductors and for calculating the currents flowing in a various conductors. So there are two laws which I stated a while ago. So these laws are the Kirchhoff voltage law and Kirchhoff's current law. So let's begin our discussion with the Kirchhoff's point law or Kirchhoff's current law. So from this law, it states that in any electrical network, the algebraic sum of the currents meeting at a point or a junction is zero. In order to understand more, let's put it in another way. It simply means that the total current leaving a junction is equal to the total current entering that junction. It is obviously true because there is no accumulation of charge at the junction of the network. In order to understand more about the Kirchhoff's current law, we consider the case of a few conductors meeting at a point as in this figure. So, some conductors have current leading away from point or junction A. Assuming the incoming current to be positive and the outgoing currents to be negative, we have I1 as positive, negative I2 as negative, negative I3 as outgoing current, positive I4 because it is incoming current, then negative I5 because it is outgoing. So, as stated by Kirchhoff's current law, this summation of current must be equated to zero. Then solving it algebraically, we can prove that the incoming currents I1 plus I4 is equal to the outgoing currents I2 plus I3 plus I5. Consider the next figure. We have the total current I, then as our incoming current I, we can see that it is equal to the outgoing current I1, I2, I3, and I4. Then we can generate again an equation using the Kirchhoff's current law from this point. We generate I is equal to I1 plus I2 plus I3 plus I4. So, this Kirchhoff's current law, we can generate a lot of equations together with the Kirchhoff's voltage law. Therefore, we can solve equations simultaneously. So, as a take note, upon creating equations using Kirchhoff's current law, the assumption or the sign of current must be fixed throughout the solution or the production of the equations.
So for today, we will discuss about the Kirchhoff's voltage law. So what is Kirchhoff's voltage law? Kirchhoff's voltage law states that the sum of all the voltages in any closed loop is equivalent to the sum of the potential drop in that loop, or mathematically, it is the algebraic sum of the potential drop of the resistances of the conductors and the currents in them in that loop is equivalent to the total voltage available in that loop. So, for better understanding, we will now proceed to this example. So, this is an example of a simple circuit. Consists of a 2 voltage source and 2 resistors, which are 1.5 decivolts, 9 decivolts, and the 100 ohms and 200 ohms resistors. So, before we proceed to the equation, we must write the loop. So, you should draw a loop. So, for me, I will choose the clockwise rotation of the loop. It is your choice if it's your choice if you want a counterclockwise or a a clockwise loop. But for me, I will choose the clockwise loop. Now we will proceed to the equation. So before we write an equation, we must know first the polarity of the components. So if the loop enters the negative polarity and exit to the positive polarity, the sign of that component will be positive. While on the other hand, when the loop enters the positive polarity and exits to the negative polarity, the sign of that component will be negative. So now we can now solve for the equations. So notice that the 1.5 volts enters the negative polarity and exits to the positive polarity. We can now write it as a positive 1.5. Now for the R1, it enters to the positive polarity and exits to the negative polarity, when we can write it as negative 100 I. For the current across here is I. Oh, I forgot to name the loop. It is named as I. So next will be the voltage source. Here we can notice that the loop enters the positive polarity and exits to the negative polarity. We can write it as negative 9. So for the last one, R2, the loop enters the positive polarity and exits to the negative polarity. So we can write this as negative 200 I. And we should equal it to 0. Now, you notice that the 200 and the 100 ohms are with the same variable. You know why? Because the current flowing to the whole circuit is the same, because they are only in series connection. So understanding that, the current flowing in them are equal. So we can now proceed to for identifying the current flowing to that circuit. So we should do the algebraic part. So transposing this 100 and 200 I to the opposite side, we will have this equation. So for this, solve it. 1.5 minus 9 is equivalent to 0. So for this, we can now solve for the I. Then I will be equal to the 0.025. So remember that I is in ampere. Oh, negative 0.025. So converting this into milliampere, we will have as you can see, we'll have a negative result. It only indicates that the loop you choose is opposite the correct loop or the current flowing in that circuit. So we should change the loop in this circuit. The correct loop will be in counterclockwise direction. So the final answer will be 25 milliamperes. So the current flowing in here and in this resistor is equal to 25 milliamperes.